Okay. So chapter 8, it's a short chapter. There's really only 2 sections that we cover in chapter 8. And it's divided up for us addressing mean value or quantitative type variables as opposed to proportion, which would be more like qualitative, right? Okay, so they do this a lot in these chapters, just like we saw it in chapter 7, where we had it divided up in that manner. So it's kind of a repetitive concept. Whatever we do today is repeated in essence when we cover it on Wednesday for the proportion, but we just tackle them a little bit differently because their formulas are a little different. So chapter 7 had us talking about, and chapter 6 in essence, had us kind of taking information and assessing the probability or the likelihood of something happening from that distribution, correct? Yeah, like we had an expected mean, we had the binomial distribution, right, where we were trying to figure out the likelihood of getting potholes in a 1 mile stretch of a city. Okay, you remember that? And then in chapter 7, we talked about normality. So trying to identify the probability or the likelihood of something happening if it came from a normal distribution. What did we find happen when we tried to put a normal concept into something that was skewed, into data that was skewed? What happened? Did it work? It didn't work, did it? Right? Okay, so that's why we had the whole assessing normality. Now, with both of those chapters, we are kind of going in and we're trying to figure out the likelihood of something happening from and make an assumption on the population. And what we're going to look at today is, well, how can I make that assumption on a population if all I'm looking at is a sample, right? You ever thought about how is it that we can, if you ever look at polling data, right, where they'll take a sample, let's say they throw something up on the news and they say whatever it is that they want to say, but they'll talk about it coming from a sample of maybe 1,200 people, let's say. Have you ever thought, how can you make this inference onto the United States population if you only talk to 1,200 Americans, right? How does that work? So what we're going to focus on today is, well, it does work mathematically, right? There is a mathematical way for us to be able to discuss this. And that's kind of the idea behind our study in this chapter, where we're talking about how does our distribution from a sample mean compare to the distribution of a population. All right, so that's what we're thinking of, sample means versus population means, or samples versus populations. And in this, we're kind of looking at the fact that we know that if you look there, we've got X bar. X bar stands for, up on the screen up there, what does X bar stand for? What does that variable stand for? It identifies what? Variable. A sample mean, right? And p hat is actually going to be the population, the sample population. But here we are talking about the mean of a sample and the mean of whether that is whether that's quantitative or qualitative. And we want to understand that the mean of the sample is going to change. So therefore, the mean of the sample is actually, in essence, a variable, right? We know from math classes that a variable is something that changes all the time, okay? And what we want to be able to identify here is we want to get in the habit of, when we say that we're going to describe the distribution, I say describe the distribution, you want to start thinking, okay, I've got to identify 3 things in that description. I'm going to identify the shape, whether it's a normal or skewed. I'm going to identify where the center is located at, right? What is the value of the center? And I'm also going to identify what the spread is. Spread is code word for what in statistics? Well, that's spread, but no, not in statistics. If the center is code word for, what's the center code for in statistics? What do I talk about when I'm talking about the center of a distribution? Mean?
would be standard deviation.
The spread would be the standard deviation. So when we're thinking about shape, we're talking about normal versus skewed. When we talk about center, we're talking about the mean. And when we talk about the spread, we're talking about the standard deviation. Those are the three things that we're going to be talking about in describing. All right. Now, everybody has StatCrunch pulled up, correct? Shake your heads, yes or no. Right? And if you don't have it pulled up, you better get it pulled up lickety split. Okay, what we're going to do is we're going to walk through a series of examples here to kind of help us understand what's going on. And we're going to look at what happens when we discuss an IQ score. So it says here that IQ scores are normally distributed with a mean of 100 and a standard deviation of 15. All right. So we're gonna play around with some data and see what this looks like based on this idea that IQ scores have a normal distribution, that they have a mean of a 100 and a standard deviation of 15. That mean of 100 and standard deviation of 15 is referring to the sample or the population, by the way. That becomes important to identify this. Population, right? Population. One of the things that should help you, it doesn't always help you, but one of the things that should help you is they're specifically saying mu is equal to 100. Mu, no mu sub x, no mu sub anything. It's just mu is equal to 100 and sigma, the little o right there, is equal to 15. Those two variables are reserved for population data. So if that's in there, you can safely assume that this information is talking about what we know about a population, okay? All right, so let's go into StatCrunch. Let's go to the applets. And then scroll down to sampling distributions. Everybody on this screen right here, does everybody have that pulled up? Okay, we're just going to work on it together. I don't think you'll have to come back and do this anytime, but we're going to see what happens. We want to understand what's going on with a distribution as I adjust certain aspects of this distribution. So I'm talking about sampling from an overall population. And I'm going to pull from a population that we know is normal. So I'm going to come down here and I'm going to click on the bell-shaped button. Because I'm going to pull samples from a normal population. My normal population that I'm going to pull samples from has a mean of 100 and a standard deviation of 15. So the setup here is, we know already we want to talk about IQ scores. The population says that the mean of IQ scores is around 100 and a standard deviation of 15. So we want to come in here and start thinking about sampling from that population. Everybody here? Okay, everybody got that done? Okay, so now we just hit compute and it pulls up this screen right here. Okay, everybody has this screen pulled up, correct? Okay. So even though I don't know if you can always see all of that, but okay. Somebody describe for me, please, the shape of the population. Everybody see where that's at? What's the shape of that population? It's bell-shaped, so there's our shape. What's the center? 100, and where did you find that? Because it says mean up there at the top, correct? What's the spread? 15, because the standard deviation says 15, correct? Everybody see that? So what we're going to look at is what happens if I know that my population is normally distributed. What happens to certain things? How can I be sure when I sample from my population that I'm moving and I can apply the things that we want to look at here? Okay, so what we're going to do is we want to take a sample of size 10. So I'm going to come in here and I'm going to change this from a 2 to a 10. And I want everybody to just hit a one-time sample. Okay, did you have all these things that dropped down for you in that middle bar there? So what happened is, let's see, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 of us, right? 14 of us went out and we talked to 10 people, right? We all had a sample of size 10. I talked to 10 people, you talked to 10 people. Did we talk to the same 10 people in essence?
No.
No, right? We're talking to 10 different people, all right? So pretend that we're in different locations, even in the city. We go out and we talk to 10 different people, and I record their IQ scores, right? In my sample of 10, I ended up with a mean IQ score of 95.041. Did you all get a mean of 95.041? Why? Because we talk to different people, right? Because we have a different collection in our sampling, correct? What was your standard deviation? Was it 14.06? No, right? No, because what we want to see is that when we sample, our sampling is in essence a random variable. Our sample is going to change from each sample that I get, right? Okay, now what happened is in this applet that we're using here, this middle band right here represents one sample that we can see, all right? And then the bottom band down here is going to end up representing the average mean, right? The average of all the samples that we look at. So for each sample, we have our own mean and standard deviation, right? Okay. Now what I want you all to do here is, let's cut to the chase. I want you to hit 1,000 times. And in the blink of an eye, we end up with this, right? We all ended up with something on our own screen. We have 1,001 samples now because we started out with our single sample. The middle band again represents the latest it would have been that 1,001 sample. This is the result of that the very last sample we did. And this green thing at the bottom now represents the collection. It's a histogram of the 1,001 samples that we just conducted. Okay? Now, does everybody understand what we're looking at here? Okay. So somebody tell me then, describe for me the shape of the sample means. Describe for me the shape of the sample means. It's bell-shaped, all right. How does it compare then to the population mean?
It's not as symmetric as the population. Well, like it is, but it's not.
It is, but it's not. Okay. Why would it not be so symmetric? Just because it's got a little bit more of it's more gradual on the left than it is on the right? Is that what you're seeing?
Yeah.
Okay. But in essence, if you could compare it between a normal versus a skewed, which one would you land on? Okay, that's good. What else do we notice about the difference between it?
It's not as wide.
It's
Not
not.
as tails.
It's not as wide. It is very narrow. That's right. What else? Where would most of the data be falling then?
Closer to 100.
Closer to the middle, right? Okay. And in essence, if we were to put these next to each other, you might almost find that it ends up getting taller, right? So when we tend to shrink the data in towards the center, we end up making it a little taller most of the time, okay? So if we've decided that the overall shape of our sample distribution is still a normal distribution, now I want you to compare for me the mean of the population versus the mean of our sample means. Pretty close, isn't it? Right? Okay, so that should be kind of comforting. If we know that we have a population with a mean of 100, and I go out and I do all of this sampling, right? I'm pretty confident then that whatever I sample is going to have a similar characteristic, a similar center as the population I'm pulling from, okay? So it doesn't change a whole lot, right? The center did not change a whole lot from the population to the sample. And we all understand that the green histogram right there is the average of, right? Each one of those bars, if we can see them, it's the average of 1,000 different samples. Each sample, 1,000 different times had its own mean, and we just did a histogram of them. What can you tell me about the standard deviation? It's lower than the populations. It's smaller than the populations. Does that, and I completely agree with, that's something, isn't that what you would expect to have happen if you're just looking at the pictures? Because did we all say, I heard y'all say that it wasn't spread out, right? So if we go from the population to the sample, and the sample is not as spread out, it's less spread out, right? Then you would assume that with less spread, you would have a smaller standard deviation, right? Because the standard deviation is telling you how far you are away from the middle. So this is saying that we're closer. Now in 1,000 samples, that's sampling quite a bit of people, right? That would be sampling a lot of people. And we would expect in statistics, and you can see the model is showing you this, right? We would expect that as we sample, the more times we sample, the less variation there is. Just in essence, the less variation you have because you're sampling more and more times, okay? So with a sample size of 10, we end up with this information here. And let me move this out of the way. I want to keep these numbers for us. All right. Now, let's go back in here. Let's reset our distribution. Okay. Let's reset that distribution. And now I want to change the sample size. Instead of us talking to 10 people, what if I increase the sample size to now be 20? All right. So we're going to increase our sample size to be 20. And we're going to do it 1,000 times. Okay. Now we have 1,000 different samples again. We all went out and instead of talking to 10 people, we talked to 20 people. And in my sample of 20 people, I have its own mean and I have its own standard deviation, and I do that 1,000 different times. This is a green histogram that represents those 1,000 samples. Okay, tell me, well, how do you describe the shape on this? It's still symmetric, all right? What else do we notice about that symmetry? What else do we know about that normal distribution, the bell shape? It's skinnier again, right? Okay, it's probably even skinnier than the last one, if I were to put them next to each other. What do we notice about the mean of the sample versus the mean of the population? I didn't hear you. Tell me again.
For the mean, they're pretty similar to both mean.
All right, so the means are pretty close still, right? So increasing that sample size doesn't necessarily change the mean at the center, does it? The center looks like it's staying the same. What do you notice about the spread? The standard deviation, what do you notice about it?
Still low.
It's even less, right? Before it was 4 point something, now it's 3 point something, right? So we got even smaller, right? We have less spread, okay? Because we increased the number of people that we talked to, and we did it a lot of times. So we have decreased the variability in our variable, all right? That's in essence what we're looking at there. Now, all of this is extremely important for us because what we can see is that we have this information about both a population and a sample. And so when we are talking about this in essence, when we are looking at this kind of information and talking about, well, how does that sample then compare to our population? How do I know that if I'm going to sample out of a population, I can feel assured that I'm going to be doing this in the correct way? Well, we can see that if we have a normal distribution, the center of my sample is going to be the same as the center of the population, right? The mean of the sample is going to be equal to the mean of the population. Notice that the symbols that we're using here, mu sub x bar. Does everybody see that? Mu sub x bar. So mu with a subscript of x bar says the mean of the sample distributions. So the mean of all of these sample means is equal to the population mean. We do know, however, that standard deviation is changing. We saw that the standard deviation was changing in relation to the sample size. So the formula that we're going to look at says the standard deviation sigma sub x bar, that's the standard deviation of all the sample means, is found, and we will need to use this, is found by calculating the standard deviation from our population divided by the square root of our sample size, okay? So our sample size was playing a role into how spread out our data was, right? Because it was changing. The mean, the center didn't change no matter what, but that standard deviation was changing, and so we have a formula now to be able to calculate that, okay? So what this says is regardless of the distribution of the population, the sample distribution x bar will have a mean equal to the population and a standard deviation with our formula there. All right, that's kind of what we're talking about. Okay, so this is kind of this idea that if I run a sample, if I pull a sample of 20 people one time and I pull a sample, say 10 years later from the same type of a population, I'm not going to get the same data, right? I'm not going to get the same information, but I can feel confident that the center of my data is going to always be close to the center of the population. And then I can adjust my standard deviation based on whatever large of a size of a sample that I chose. Okay, those are key important concepts for us. Okay, now let's use this idea right here. It says, I want to know what the probability is that if I take a random sample of size 10 for the IQ problem, what is the probability that in that sample of size 10, the results of our sample mean is greater than 110? In other words, if I go out and I sample 10 people, what's the likelihood or the probability that my sample mean is 110 or more? What's the likelihood that in my individual sample that the mean of my sample of 10 people had a mean greater than 110? Okay, now when we're looking at this, we're going to take this problem, which is a normal distribution type problem, right? Because it tells us in here. And let's first identify some things as I'm trying to pull up the right thing here. All right, so we want to compute the probability. In other words, what we're going to be doing is computing this probability statement right here that I just highlighted. What is the probability that the mean of my sample, x bar, is greater than 110? Now, that's going to be the same process as us finding the probability of a normal distribution that we did last week, right? 7.2, we were asked to do exactly the same thing. We wanted to know what was the likelihood that my random variable was going to be greater than or less than something, right? Okay, so it's not any different, but we want to make sure of a couple of things. First of all, we want to identify the fact that it says that our IQ scores are normally distributed. We already know this because we just played around with these numbers. But what I want you to get in the habit of doing is, okay, what is this shape? Remember how we were talking about this? We need to be able to describe the distribution before I ever go and do any calculations on it, okay? So the shape of our distribution is going to be normal, right? It's going to be normal because we're told that the population is normal. Okay, the center of my sample, the center of my sampling distribution, let's say, the center of my sampling distribution is going to be equal to the mean or the center of the population, which was 100, right? And then our spread comes from the standard deviation of the sample means, and that was equal to the standard deviation of the population divided by the square root of n. The population's standard deviation was 15. The sample size we're using is 10. Okay. So let's just take it to, I don't know, 3 decimal places. I want to know what is the, I need you to find me that number to 3 decimal places. Okay, so 15 divided by the square root of 10. Hopefully you come out with a number that would be I only have 2 decimals, 3.35. That's your goal. You have something that's close to 3.35. Really? I'm looking at the wrong number. 4.74? Okay, maybe I'm looking at the wrong example. Oh, I am, sorry. That's why you didn't get it. All right. Tell me what you thought it was again, 4 point something? 4.74. All right, so that's our standard deviation. Ignore what I have written up there. My pen doesn't really want to work for me right this second. Now we need this information because what we want to talk about is, we want to know, remember this is a random variable. We know that this is a normal distribution. So when we ask this probability statement like this, we're saying, what is the probability that I have a sample mean? So my mean of the population is 100, and therefore the mean of my sample means is going to be the same thing, right? The mean of the population and the mean of the sample means are going to be the same. And what is the likelihood that when I go out and sample, my sample mean is greater than 100? That's what we're looking for, correct? So remember this distribution that we're looking at, the one that I drew up there, is what we say is happening to, if I were to repeat the process of sampling people of size 10, right? If I was to repeat this process over and over and over again, the shape of my distribution looks like the one I drew up there. What is the likelihood that if I were to now go out and sample, I would have a mean from my individual sampling group, what's the likelihood that my individually sampling group has a sample mean greater than 110, okay? And how do we find that? This is a normal distribution and I'm asking for the calculation based on a normal distribution. What calculator did we use for that? The normal calculator, right? The normal calculator. So we go back to StatCrunch. I go to stat, calculators, coming down to normal. This looks almost the same. I mean, the calculator is the same, but we handle it now differently. What mean are we using that we just wrote down?
100.
Okay, so the mean that we put in here right now is going to be the mean of our sample means, mu sub x bar, which we said was the same as the population. What's the standard deviation I'm now going to put in there? 4.74? Because that's the standard deviation of the sample mean. What's the likelihood I get a sample mean back that's greater than 110? 0.0174. 0.0174. Did you put the right standard deviation in there? That's my fault. All right, so here we have the likelihood then that I am going to, so the probability of obtaining a sample mean greater than 110 from a population whose mean is 100 and standard deviation is 15, right, is approximately 0.02. Okay. We would expect if we were to repeat this process, right? If we were to repeat this process 100 times, then with samples of size 10, then we would expect 2 of those samples to come out having a mean greater than 110. Okay, see that? Yeah? Okay. So that's pretty straightforward in essence. You kind of just have to start wrapping your brain around what am I testing here? We move away from testing on the population because the likelihood of us having population data is not as high as it is sample data, right? I don't always have, in fact, it's less likely for me to have the full data set of an entire population. It's more likely I have sample data. So what we're fixing to start doing in chapters 8, 9, and 10 is we are addressing information based on sampling, okay? We're addressing information based on sampling. So what we've learned is that if the population is normal, then when I sample from the population, I have to adjust some of those formulas, but in essence, it's the same concept. If I started out with a normal distribution, if I started out with a population whose mean was 100 and a standard deviation of 15, then I would expect, if I repeated the process 100 times, I would expect if I sample, I would get 2 samples that would have a mean IQ score greater than 110. Okay, does everybody kind of starting to see it, even though I've said it? I just keep saying the same thing, but do you understand what I'm saying? Okay, well, that's all fine and well, but let's see what happens now. Let's go back this way. And let's see if I can change this. Okay, so this is the same concept as what we were looking at. What is the shape of this distribution? Right. What is the center? 14, right? 14.05. That's the mean. What's the spread?
11.82.
All right, 11.82. Okay. So let's say that I want to sample, I don't know, let's go 10. No, let's do it. Let's do 5. Okay. Notice that if I were, I don't know what, I'm just making this up, right? I don't know what type of a skewed data we're looking at. Let's say it's housing prices or something. I don't know, that's usually skewed, right? Okay, and I go out and I sample 5, I have a sample size of 5, right? So I'm only looking at 5 things in my sampling, and I repeat this process 1,000 times, okay? Notice that this is our population at the very top, and at the very bottom is our sample, right? That's the result of 1,000 different samples. The population data is skewed. What do we notice about our sample distribution down there? What's the shape of it? Still skewed right. Is it as skewed right? Not as skewed right, right? What, ma'am?
Significantly closer to ocean.
That's right. It is significantly closer to bell shape. That's correct. What do we notice about the center between the population and the sample? The mean. What's the difference between the means? They're very close, right? So the center stayed about the same as far as the mean was concerned. How about the standard deviation? Right, it's much less, right? It is so what does that mean? That this data is not quite as spread out, right? So we have a smaller spread, but we're still not quite normally distributed. We're still fairly skewed with a sample of 10. Let's change this to 15. Now what do you notice? Tell me about the shape. There aren't that, the other one had what looked like kind of some outliers on the right, correct? So it's still pulling it to the right. Now I don't really see those, correct? There's not as much data in it, and there's not really tails on these things. What do you notice? And what do you notice about the height? Kind of tall, right? All right, what do you notice about the means? The mean of the population versus the mean of the sample? Almost the same though, correct? What about the standard deviations? Less, way less. That's right. Okay, the last one let's look at, because that's pretty good. I would say that's pretty good. Let's say 40. Now it looks pretty good, doesn't it? Looks pretty symmetric right there. Okay. The means still have not changed, have they? Okay, so that's something that's important. If we don't really know what the shape of the distribution is of our population, if I don't know if it's normal or skewed, okay, at some point, I'm going to get to the spot where it's not going to matter because the center of those distributions is always going to be the same. Okay, that's good because we use the mean on certain things. We know that the standard deviation is changing, right? The standard deviation is changing. Now, what we learned, and we alluded to this last week, is that we have this central limit theorem. All right, we have this central limit theorem. Okay, and it's basically right there in the center. The central limit theorem is a key component too. It's like the underlying component to most of our statistical concepts that we're using. This idea that the shape of our distribution is going to become more normal, right? That shape of our skewed distribution started to become more normal as I was increasing the sample size. The larger the sample size, the more normal our distribution got, wasn't it? Okay, we started out with 5, then we went to 15, and then we went to 45. okay? And as I increased it in each time, that shape started to take on a more normal distribution. That's what the central limit theorem tells us. It tells us that if the distribution of our population is either not normal or not known, then our sample distribution can become approximately normal, right? Regardless of our shape, we're going to have an approximately normal distribution. Here, let me move that up here. This is where I want y'all to start seeing it. That is the definition of the central limit theorem, okay? That regardless of the shape of our underlying population, no matter what the shape is of our population, sampling distribution becomes normal as the sample size increases. Now, you don't want to increase your sample size so large, right? There's like this balancing point, okay? This number says for n greater than or equal to 30. So there's kind of like a number out there that says, all right, if your sample size is greater than or equal to 30, then it doesn't really matter if the population was skewed or not. It's going to, for the most part, be a normal distribution. And we saw that starting to happen when we chose 15 for our sampling distribution a minute ago, but yet I still upped it to 45. So there's just this number, it's kind of a sweet spot, doesn't mean that it's always going to happen, but this number at 30 says, all right, if your sample size is greater than or equal to 30, then you can kind of guarantee that you're looking at a sampling distribution that's going to be normally distributed, okay? That's what the central limit theorem says. It only has to do with the shape, right? It only has to do with that shape moving from a skewed to a normal distribution. But those formulas don't change, right? Those formulas don't change. So regardless of whether my underlying population was skewed or not, the mean of the sample is going to be equal to the mean of the population, and the standard deviation of the samples is going to be given by that formula right there, dependent upon your sample size.
So why did you put the
That's the rule. So we're gonna, typically you'll be asked, you're gonna have a question, I'm sure, on your homework that says, you'll walk through this example and the sample size will be less than 30, but you don't know anything about it. So was that a good choice, in other words? No, not really. You want to make sure that your sample size is greater than 30. And if it's not greater than 30 in the real world, right, if you don't know what the distribution looks like of your sample, of your population, and let's say, I can see this happening on like studies where you're retrospective type studies, right, where you're looking at somebody else's data and maybe you don't know anything about it. You would just try to see, okay, well, I don't know what the overall population is of this. So if my sample size is not greater than 30, is there a way for me to increase the sample size? Because if you can increase it to 30 or more, it doesn't really matter what the population was. Okay, so that's kind of the conclusion that you would make. Okay. So this question is actually on your papers that I gave you, but we're going to work it together. Just because I think it's a fun one to work. Okay. So this question is saying, suppose an elevator has a maximum capacity of 16 passengers with a total weight of 2,500 pounds. Assuming a worst case scenario in which all passengers are male, what are the chances the elevator is overloaded? Okay, how many of y'all notice, right, when you stand in the elevator, there's that little placard that'll tell you the capacity size. You know what I'm talking about? We're all staring at something other than the people you were in the elevator with, right? The floor, your phone, something, not making eye contact. Okay? So this reminds me of that. And it'll tell you a maximum weight. Sometimes it'll tell you the maximum number as well. Okay. So for this question, it says here, assuming that male weights follow a normal distribution, we have a mean of 182.9 pounds and a standard deviation of 40.8. So let's look at that for just a second. And I want to kind of ask yourself, let's set this problem up, okay? We want to find the probability that one randomly selected male has a weight greater than 156.25. Okay? Now, a couple of things here. What we're looking for, the question says, what is the probability that some male, that's just a variable X, some guy out there, has a weight greater than 156.25? Now, in the passage, it told us that male weights follow a normal distribution. So the shape of male weights is normal. The mean is 182.9. What variable am I going to assign for the mean?
22.9.
Mu? Yes, because it says the mean. 182.9. What variable am I going to assign to the 40.8? Sigma. 40.8. Right? And this question says, what's the probability that one randomly selected male has a weight greater than 156.25? Now, this 156.25, does anybody have a clue where maybe that number came from? Was it completely random? Just look at the first part of that problem for a second. Anybody have an idea where 156.25 came from?
$2,500 divided by 60.
Right, okay, so what this is saying, it wasn't just completely random. What this is saying is 2,500 pounds divided by 16 passengers means that each passenger would be 156.25, okay? That's where that number came from. It's kind of important, I think, in the problem. So what this question is asking is that, well, I'm going to ask you, says find the probability that one male has a weight greater than 156.25. Is that question a question about the population of males, or is that a question about a sample? It's a question about the population, because it simply says find the probability that one guy out there in the whole world of males weighs more than 156.25. That's important because that tells me that the mean that I'm going to use in this case is 182.9, and the standard deviation I'm going to use in that case is 40.8. When we go to our normal calculator and we find a mean of 182.9, or we have a mean of 182.9, we're saying, what is the likelihood that some guy out there weighs greater than 156.25? Okay? You've got the calculators pulled up. What do you find?
7,431.
Does everybody agree that it's 0.7431? Yes? Everybody did it? So what does that mean? Somebody interpret that for me.
Probability that one randomly selected male in the elevator would have a weight greater than 156.25 pounds, 0.74.
take issue with one part of that, because everything's correct in essence, except we are not talking about the 16 people. So what this is actually saying, and it becomes important for us to be able to differentiate between a question asking about population and then a question asking about sampling. So this question really just says that, okay, in the whole world of men weight, the likelihood that I encounter a guy who has a weight more than 156.25 pounds is about a 74% chance. All men, right? And think about men that you know, right? The likelihood that these people weigh more than 150, that men weigh more than 156 is approximately 74%. Okay, in general. Right? That's what this says, according to their normal distribution, according to their standard deviation and their mean that this comes from, okay? So the chances of us encountering just some guy off the street, right? Okay, the second question says, find the probability that in a sample of 16 men, that their weight would be greater than 156.25. So find the probability that if you have 16 men standing together, right? The elevator opens up. This is a better visual. The elevator opens up and 16 men are standing there on the elevator. Find the probability that they're gonna weigh more than 156.25, right? What's the likelihood that I'm gonna get 16 men together that weigh more than 100 and each one weighs more than 156.25 is what we're doing. So this question is now asking about a sampling distribution. So this question says, what's the probability that the average weight of these men is greater than the 156.25? Well, what is the mean of my sample mean?
Over 180.
Exactly, because the mean of the sample is the same as the mean of the population. What's the standard deviation of the sample mean? The formula.
40.8 divided by the square root of 156.
The sample size. So 40.8 divided by the square root of 16. And what do we have for that value? 40 divided by 4 would be 10 something, right? 10.2? Okay. Is that what you said?
Yes.
Okay, I couldn't hear you. 10.2. So these are the values. This mean and this standard deviation is what we're going to put into the calculator, right? The normal calculator. That's what we're looking at here. Okay. So what is the likelihood? What is the probability that a sample of 16 men have an average weight greater than 156.25? Point 9956, is that right? Is that what you said?
We'll just point.
All right, 0.9955, 0.995, 0.996. Feel like I should say 199. I'm gonna say it. All right, so what does that mean?
99% probability that will
That the average weight of 16 men is greater than 156.25, right? So that means that when that elevator door opens up and there's 16 men standing right there, you're gonna go, nope, not getting on that thing. It's gonna crash to the bottom if we get on it, right? Okay, well. So it's a 99% chance that you're gonna get 16 men together and that their average weight will be greater than 156.25. It's a 75% chance that you encounter one man that has a weight greater than 70 or 156.25. Do you see the differences? Okay, that's sampling, right? I want to know what the average weight is of the 16 men. You might have people that weigh more than 156, you might have people that weigh less than 156, but the average of the 16 men is going to be greater than the 156.25, which means that you have exceeded that capacity, right? Next time you're on an elevator, that's a fun one to think about, okay? Okay, so with these problems that you're gonna be encountering as you go through, you want to pay close attention to, is the question about the population or is the question about the sample mean, right? Are we looking at a population question or are we looking at a sample question? Okay, so we have about 20 minutes left. On your paper, I would like for you to try to do questions 1, 2, and 5, I believe are the ones that you have on.